All right, good afternoon. Everyone full from lunch, hopefully, and still awake. Hopefully you are here for visualizing endpoint security using Apple's 2D game framework. That's a lot, but I'm told this is going to be super exciting. I'm Eric Blakely. I'm a consulting engineer here at Jamf, so thank you for coming in. Just a quick reminder, I'm sure we're all used to it now, but Q&A on the app, and then we'll facilitate that at the end. And with that, I will introduce Maggie and Jaron for their presentation on something amazing that they've spent just a hot minute building. So welcome on.
Thank you. All right, cool. Yeah, hello everyone. And yeah, as was stated, welcome to a mouthful, visualizing endpoint security using Apple's 2D game framework. About as straightforward as we could get. That's honestly what the whole talk's about. We spent a lot of time building an app, and we're really excited to show it to you. So my name is Jaron Bradley. I'm director of the Threat Labs team here at Jamf for macOS specifically. And I'm speaking with my good friend Maggie, who will be on in just a bit to kind of introduce the tool. But yeah, really excited today to talk to you about a tool that we are calling SpriteTree. So SpriteTree is a tool. It's built on SpriteKit, Apple's 2D graphics engine, if you couldn't guess that. If you've seen my talks in the past, you know that I put a lot of emphasis on the process tree for incident response or just for threat hunting in general. And it's because the process tree can provide us with a lot of context into what's actually happening on the system, what software is doing, what actions are occurring. It can all be tracked back to specific processes, and those processes and the trees that led to their creation are ultimately where we get all our context from for threat hunting. So we want to look at some of this software, or in our case, malware, where we use tools like this a lot to try and determine what malware is doing and how it's behaving. But before we get into that, we kind of want to start with a bit of a problem statement that is like basically get into why is this tree so important. So the first portion of this talk could be a little dry. I promise we're going to get to the good stuff, but we do want to start with a bit of the problem statement. So why does the process tree matter? Well, to explain this best, I usually give a very specific example, and that is the etc sudoers file being modified. So the etc sudoers file, if you're not familiar, it's a system file that controls which users are allowed to escalate to root on your macOS device. So knowing when it's modified is probably something that you might want to be aware of, right? But knowing it's modified in and of itself doesn't necessarily help us. There's a lot of missing context into the why and the how it was modified. So this is why, and the why and how of this is often provided through the context clues via the process tree. So for example, here you can see that Vim was responsible for modifying the sudoers file. Vim, we know, is a shell-based text editor that's used for modifying files manually. So we know that whoever modified the sudoers file did it manually via Vim. To gain even more context here, if we look further up the tree, we see what's a pretty common process tree when something like this happens, right? We look up, we see that terminal was somewhere towards the top of the tree, and that tells us that this was likely an action performed by the user who logged into the graphic interface of macOS. They opened a terminal, they ran Vim to modify the sudoers file. But things change a little bit if we discover that etc sudoers was modified by Vim running under SSH, right? Some power users might log into the system and modify SSH this way, but your standard user is not going to have any idea of really how to do this. But it is a feature that is there for legitimate purposes if you want to do it. But now we might want to investigate. Should somebody be SSHing into whatever system this happened on? Is this something that should be a normal thing? There's a lot of other context hidden in the process tree that tells us that. But how about this scenario, like this, where we see the Jamf daemon modifying the etc sudoers file via an echo command, right? I see this, and at a first glance, I'm probably like, okay, this is probably an admin script of some type of action that the admin's taking to modify the sudoers file. Kind of interesting, and I might assume it's admin and kind of push it aside. But if we look at the siblings of the bash process in this process tree that went on to perform other actions, we might think otherwise. So we see netcat in this case at the top, right, NC. This is the TCP Swiss Army tool of macOS when it comes to making TCP connections. And then under that, we see the DNS-SD command. This scans the network for open bonjour services that might be running on other computers that they're emitting. We've seen that used by attackers as well. And in this case, I might no longer assume it's an admin because I've looked at the siblings. I'm now assuming maybe somebody's doing something weird with Jamf Pro that I don't really want to be happening, and I should double check who has access to this, right? So these sibling events of a process tree tell a story as well. So we're going to focus a lot on process creation. We can get process creation events from the Endpoint Security API, and there's two different types, fork and exec, and it's good to understand both of these. So we're going to spend just a little bit of time here, quick crash course. Let's say that we've built an executable that wants to go on and it wants to get the output of, say, the whoami command. I don't know why, but it wants to use, whoami. It wants to know what user is logged into the system. At the lowest level of macOS, when you create a new process, what you're actually doing is forking your current process. So forking means you're cloning the current program, which gets the same executable, but running a new process ID. So we had PID 123 for our original program. It forked, and now we have PID 124, but with the same program. That clone will then go on to run the executable that you've requested, but notice it has the same PID as the clone that created it, PID 124 in this case. This is because when the exec goes on and gets carried out, that exec overtakes the clone that was previously there. This is at the lowest level. If you're coding in Python, if you're coding in some higher level languages, this is all handled for you. You wouldn't even be none the wiser that has happened. This is what happens ultimately, leading to, if you're collecting processes in real time, we end up building a tree that looks like this, which is not super helpful to us. Again, this is part of the problem statement. In reality, what really happened, and in terms of representation of what we would want to see as threat analysts, we would want to see something more like this. Yes, there's two PID 124s, but the first one, the fork, went on to exec the actual whoami. So that's just one issue when it comes to collecting processes and threat hunting. There's a whole nother issue in that the architecture of the operating system and the way LaunchD schedules nearly everything on the operating system. This leads to a very one-dimensional level tree, and let's kind of get into this, because this is another part of the problem statement that we kind of set out to solve. So LaunchD, if you're not familiar, really quick run through. Don't have all the time to cover all the details, but LaunchD was a program added to the Apple ecosystem in 2005. It was basically meant to be the ultimate scheduler on the system, right? That could handle the booting of the system, as well as replace a lot of the scheduling software that came packaged with BSD at the time, which macOS is now based on, still based on, I should say. So for instance, your cron, your @task, your RC scripts, any of the scripty-like stuff that used to be for persistence should now be kind of moved into LaunchD. A lot of the scripty-like stuff has been deprecated over the years, slowly moved out of the operating system. Some of it still works, but overall, if you're scheduling persistence on macOS, it should be done in some manner through LaunchD. So one of the new great things that we get out of this change to LaunchD was the addition of launch daemons and launch agents. You might be familiar. Basically, we as developers or users can create a plist launch agent or daemon that tells LaunchD what to run when the system starts up. What additional software do we want it to run when the system starts up? So here you see I've started something called some service at startup, right? You might hope that when looking at processes, there'd be some clear indication of the fact that some service was started due to a scheduled launch daemon that we created. Coming back to our problem statement, there is not a way to tell this. All we get is that we get to see that LaunchD ran something called some service. In fact, LaunchD goes on to create almost all new processes on the operating system. For example, here you see me in Finder, and I open the books.app application. again, what we might hope to see is something like this, right? Somebody opened Finder, then they opened books.app. This tells us a story. This tells us a user went into their Finder and they opened an application. Instead, what we see is simply this, that LaunchD opened yet another application. This is because when you select an application using Finder, an IPC message is sent to LaunchD, which tells LaunchD to open that new application that you requested. So LaunchD complies with this request, assuming permissions are appropriate, and then we have our new process. But this leads to a process tree, once again, that gives no real context into how the books.app came into existence. Let's peek at one more example here. Let's say that our user has opened Safari, right? And they are browsing around on the internet. Whatever, they go to a website, and they download an application, and then they open that application by launching it through Safari, in this case, like so. As threat hunters, we would, of course, hope to see the process tree look like this. But once again, Safari has sent a message to LaunchD, and LaunchD has opened that application. So hopefully you kind of see what I'm getting at here with the problem statement, is that when you look on your operating system at the running processes, nearly every single process is LaunchD, and we get a very one-dimensional process tree that doesn't tell much of anything. At any given moment, this is just me running, and looking at the processes on my system, but 94% of the processes all had a process parent of LaunchD, or process ID 1. So for this reason, a while back, I created an application called SpriteTree, which can be downloaded from my website, themittenmac.com. I still host it there. I still manage it and try to keep it updated so that anyone can go grab this and build a more useful process tree. So SpriteTree, I know it's going to be hard to read, even for me standing right here next to the screen, but it goes through and it basically it works like an enhanced PS tree, kind of, where it tells you what launch daemonplists cause processes to open, as well as what network connections that certain processes have made, as well as, again, trying to make those better parent-child relationship connections. So here, for example, you can see that Finder was created above it by a finder.plist. It then went on to launch Xcode. So through Finder, I opened Xcode, and through Finder, I also opened the Pages application. If we scroll down just a little bit further, we can see that the doc process, aka the doc at the bottom of your screen that holds applications, right? I opened my Keynote program from doc, as well as I opened Safari from my doc. So I invented SpriteTree to just tell a better story than what macOS is providing. So again, that's a command line tool. Put it together a few years back and maintain it for those that want to kind of use it and play with it and see what's going on with macOS. But the question remains, how does it actually build this tree where every single parent isn't LaunchD, right? It does this using some private API calls. So when you run SpriteTree, it'll send messages to LaunchD, ask for some information, get that information back, and then build the tree out accordingly. Among the different things it collects are what you're seeing here, but most importantly, and what we're going to kind of focus on, is the responsible PID, because this is a big one. This is an important one when it comes to something that Apple provides. So it is a macOS-specific process ID, so instead of parent process ID, there is also responsible process ID. It's used majorly for determining what application should hold specified permissions. So for example, many of us are familiar with security and privacy controls, right? That require us to approve an app to be able to record the screen or the webcam, or even access to certain files. The responsible PID is kind of used to control this information. I'll give you an example here. So here you see me attempt to access the message.txt file sitting on my own desktop from the terminal, and I get this operation not permitted alert. Right? If you're an admin and you open up your new laptop, you're probably familiar with this, and you're like, oh, full disk access. I gotta hit again. But here I'm denied access, and I don't get it. So if I go into my system settings, and I then go to the terminal, or iTerm, whatever I'm using, and I make sure that iTerm has permission to access the desktop folder, now we see that the problem has been resolved. But there's still a question at play. If I didn't actually give cat, right? cat is the executable accessing message.txt. I didn't give any permissions for cat to do that, so how did macOS know to allow this to happen? Well, here's what happens when we monitor processes in real time and take a look at what's going on the operating system. You can see here that I run the cat command down low, and up top you see the events that we're getting back from the Endpoint Security API. First, we see the cat command that I executed shows up as an event. We can then see that cat has its own PID of 25023. And then we see it has a responsible PID value, that's 24417. If we were to take this PID and look it up, we would see that it belongs to iTerm. So this is how macOS is tracking what processes should and shouldn't have access to various permissions, is by using this responsible PID and determining if that's been granted permissions yet. All right, so enough yapping on the problem statement. Essentially what we wanted to do was create a true tree of sort for active running process captures. Instead of just a one-time snapshot that true tree provides, we wanted to give something where basically you could do a real-time capture on your system and then look at the process tree that was generated over time. So this isn't entirely possible in the exact same manner, but a lot of the provided PIDs that we needed are, including the responsible PID, and we also get to track forks and execs in real time, which in some ways makes this, what we were able to build, even more powerful than just true tree. So this was a brainchild of 3 different creators: myself, Maggie Zernhelt, who will come up in a second, and a good friend of ours, Matt Schott, who unfortunately couldn't make it here to JNUC because he lives very far away. So it would have been a long flight for him. So we're pitching on his behalf, and he's with us in spirit. So yeah, we wanted to make a tool users could perform analysis on and not really have to worry about all the lower level details going on the operating system. So to explain how we kind of went about doing this, I will have Maggie Zernhelt introduce SpriteTree. Oh, and you need the clicker.
So here you are looking at the SpriteTree application, which is written purely in Swift. As mentioned, it uses Apple's SpriteKit framework to display the endpoint security data. You might ask why we went about building a process tree visualizer when there are so many already available, but the ones that are available already usually depend on HTTP and JavaScript, and we wanted something local. So we were able to keep this entirely native, and we did not use any third-party libraries when creating this, so we maintain full control over what's going on here. Not only that, yeah, but we're able to add anything we want in the future due to that, and get access to all of the added benefits that Apple's SpriteKit provides us with. So let's look into how it works. First, its primary purpose is to take data captured by Apple's ESLogger tool. This command line tool was added to the operating system in Ventura, so you can perform a capture on any system running Ventura or later, and then load it into the SpriteTree app. So you'll see here that we're calling the ESLogger tool to start a command capture. Next, you can see that we specify the kind of events that we want to be looking for. So we wanted to collect some process information, so we're looking for fork and exec events. And additionally, we want to look into some file events, so we are collecting create and rename events as well. Finally, we will redirect the output to a JSON file. All right, so now we're officially recording events that are occurring on the operating system. So let's start generating some user activity. We're doing a few things here in our terminal.app window, like using the last command, ifconfig, we ping the localhost, we run the whoami command, and we check if there are any Jamf processes running by grepping the process list for Jamf. So let's open a new tab now, just for the sake of doing something interesting. And we will first use the touch command to create a file in the temp directory, and then we will move that file to the desktop. And SSH is interesting. Let's look at how to use it. Once we figure that out, we'll quit and we'll SSH into our own machine, which doesn't seem particularly useful, but it's for display purposes. So, and then finally, we will cat this little Easter egg Lord of the Rings calendar that exists natively, which is kind of a fun detail. So now that we've got the data, we can load it from any system where we collected it into SpriteTree on any other computer or the same computer. And you'll see after we load it that we're immediately greeted with a process tree for the events that took place. So by default, the process tree will be based on the standard process parent processes, which, as Jaren mentioned previously, doesn't really give us an easy understanding of what the user did on the system. For example, here you can see that we just have a terminal process hanging out by itself. It's technically accurate, but it's not really very helpful. So we know that we can use the other available process IDs to build a more helpful tree, again, like Jaren mentioned before. So by pressing Escape, we can open a menu in SpriteTree that allows us to select a PID to build the process tree by. We'll opt for True Tree here because, remember, this tree is going to use all of the different available process IDs to build a tree that we think is the most helpful. It will first link forks and execs appropriately, and then use responsible PID to build relationships between those processes. And if the responsible PID doesn't provide the context that we're looking for, then we will fall back onto the standard parent process ID. And as you can see, this provides a helpful, much cleaner process tree that now we can analyze. So one of the first things that maybe you'll notice when we open this tool is that some of the nodes have a smoky effect, and others don't. This is because we built the tool so that fork events would stand out, and fork events have this smoky effect. You can also tell by the fact that the parent processes of the nodes with smoky effects have the same name as the nodes with smoky effects. So again, another way to tell that they're fork events. If you look at the process tree, you'll notice we're looking at a branch for the terminal that we opened. First is a list of commands that were executed in the background when we opened the terminal. And next, we can see that these were the commands that we executed in the first terminal tab that we opened. We will go ahead and click on the ping node, and you'll see that when we do that, two things happen. First of all, the path to the node is highlighted, which is helpful when the process tree is large, just to catch your eye. And then the second thing that happens is we get a new button at the top that allows us to view the details of this node. So you can see in the detail window the arguments that were executed with this command, which is very helpful, as you may know. In this case, you probably recall that we pinged the localhost once. So as an analyst, I said this was helpful, and this is something that analysts end up doing a lot, kind of over and over. So the benefit here is that we get to see other commands executed in a properly formatted tree instead of the confusing tree that the standard process IDs generate. Let's scroll down to the second terminal tree that we see here. And we see some of the basic commands that we executed. But what jumps out to me, and maybe to you as well, is that we see bash was executed here, when pretty sure we just ran ZSH. So if we dig into this and look at the details of how this came into existence, we can see with the details that this bash process actually belongs to a shell script. This is due to the fact that the man command is not actually a binary, but a script. A shell script. It kicks off a bash instance. And then every command that runs within that shell script ends up launching a new process. I found it interesting. So that's a crash course on moving around the tree and browsing the data. So now we have a few other bonus features that we included. For example, you may have noticed in the settings menu earlier that we have the option to color the tree by 2 different PID fields. One field is the process group ID, which we didn't really have time to cover. But the other one we did talk about, responsible process ID. This is helpful because the coloring, as you may recall Jaren mentioning earlier, can help you identify which nodes have the same permissions. So yeah, that can be definitely helpful when thinking about malware and what can do what. So for example, here you can see that all of the processes that were run under the terminal are the same salmon color. So although terminal has 2 large branches of commands open, we can see that they all share the same responsible process ID. And therefore, every command run in this terminal is operating with the same app permissions. So in other words, if terminal.app application has full disk access, then every command with the salmon color has it as well. The same applies for any other permissions like screen recording, keyboard capture, webcam, microphone, etc. And this is how Apple intended it to be. Once an application is opened, that app should only be able to do things that the user has specified for that app. Any way to get around this would be considered an exploit. For example, maybe you remember when we ran the SSH command to log into our own system. This technique was seen used by malware a few years back in order to gain full disk access. The malware did this because when you log in over SSH, even into your own local host, you end up generating a completely different tree under the SSH daemon, resulting in a new set of active permissions. Green here. So you can see that when we catted Lord of the Rings after SSHing into our own system, that it ran under the SSHD service instead of terminal. So by default, SSH used to be run with full disk access until Apple changed it. So malware could easily gain full disk access by using this method of SSHing into the system that they were on. So that's a basic introduction of SpriteTree, and I'll pass it back to Jaren now to cover some real-world examples of malware being analyzed through SpriteTree.
Is my lapel still working? Can you hear me? All right. Just going to leave this here. Not going to drop the mic. Okay. So yeah, let's get into an actual, a handful of malware samples here. Now, in the case of all these malware samples, I detonated them while recording the ESLogger command that you saw Maggie run earlier. So if you're going to do this in your own environment, just run ESLogger, collect the forks, execs, renames, and creates. We'll have a blog post that also walks you through this at some point once we do release the app come soon. So we're going to start off with Atomic Stealer. Atomic Stealer is a piece of malware that does what you might think based on the name. It steals your stuff. Basically, it performs some recon on the system, checks some things, checks for the different cryptocurrency wallets you might be running. And then if it discovers you have some, it zips it all up and sends it off to a server somewhere. So we'll do what Maggie mentioned. We'll use TrueTree mode just to kind of get instantly into what we're saying is the most helpful visually. If we're looking at this, there is something that jumps out pretty quick at us. Again, not sure you can read that or not at the moment, but that is the fact that there is an app running on the system called application.app. I immediately have interest in that, and I want to take a look at that. Somebody's being really vague and a little generic with what they're calling their application. One additional feature that we have is to be able to focus on a specific tree. So in this tree and with this malware, I can actually tell you everything is spawned under the same branch. So if this was a large tree, I might want to collapse it down just so that I'm focusing on a specific branch of that tree. So collapse will help you do that and basically kind of remove some of the other noise for you. But here we see that an AppleScript one-liner was executed from within this app. By looking at the contents of the command line, we can actually see what's happening. It's one of the benefits of somebody trying to run AppleScript one-liners. We get to see them in plain text. So to date, this is still probably the easiest way to get somebody's password is by simply using AppleScript to ask for it. Right? Next, it performs some interesting checks that almost no malware ever does. It uses the DSCL command to test if the password that was typed in by the user was actually the correct password. You can verify this using DSCL. And the reason the malware author does this is because if the wrong password was typed in, this entire attack falls apart. The keychain can't be decoded, which is ultimately kind of important to stealing your crypto. Next, we see some pretty generic recon that occurs, which we can see by all the commands that end up getting executed. So I'm just kind of clicking through some of these. We see a system profiler check that gets, or a syscontrol check that gets used to check the CPU architecture. We see system profiler. There's this whole section of this malware that checks to see if it's running inside a VM or not. If it isn't a VM, it's going to kill itself so that you don't see anything additional that happens. It runs PS, it runs SWVers, system information, running processes, and things like that. Finally, there is a system profiler command that I actually think is a pretty cool addition by the attacker. And this system profiler command will give you a list of all the installed apps that have been registered on the device. So this is actually instead of crawling certain directories or looking what's in the applications directory, seeing what's in the downloads directory that maybe the user forgot to move to the applications directory, this is just like, hey, give it to me all in one. And then the attacker can look for the specific apps that they care about stealing from. Then ultimately we see that at the end of this application, basically an error message is fired off, doing the same kind of Apple scripty nasty stuff, right? So malware historically uses this technique quite a lot where the user runs an application, it's supposed to do something really cool, but instead it just throws up an error. And now when you can't figure out why your app doesn't work, you just move on with life and assume nothing bad happened, when in reality, a ton of bad stuff really did happen. Keep in mind, this application is running its own code as well, right? So not only can these child processes perform different actions, we of course have to worry about what the compiled application itself is doing. And if we go inside the context events, which when you click on an application, it will tell you if there's any context events, in this case, create events or rename events, file events that the application performed, we can see that it created a result.zip file. So a file that presumably has all our information in it and has now been shipped off, never to be seen again. So that's kind of one example of a recent malware that was out this year. Really quick, I want to touch on Rust Bucket malware. I'm going to skim over this one kind of quickly because immediately following this talk, almost immediately, there's a talk that dives into the full details of this North Korean malware that we found earlier this year. And you're going to get most of the details there. That's going to be in Ballroom F, and be sure to check it out. It's going to be really good. So with Rust Bucket, well, first, what do we see? Well, right off the bat, we see a large tree here that starts with something named, again, no, it's hard to see, but it's just called Applet, right? And for those that don't know, if you build an application with AppleScript and then you compile it into an app, by default, the name of the binary will be Applet. So when somebody launches it, we see that Applet ran. So here, I already know I'm dealing with a piece of software built with AppleScript just based on the file name and the node name that I see. This AppleScript goes on to execute 3 commands, curl, unzip, and open. For those that haven't spent much time analyzing malware, this is something you very much don't want to see happening on a user's system. We see here that this curl command goes on to download something called 1.zip. And we can see that once again by the create context events that happened within this process. We might suspect that the unzip command, or as we might suspect, the unzip command that follows then takes this zip file that was downloaded and unzips it. As the unzip occurs, we see the application being unzipped by the name internal PDF viewer.app. This seems weird. It's pretty smart on the attacker's behalf, right? It means that their AppleScript dropper, if it's ever discovered, all they have to do is tear down a link somewhere that curl reaches out to, and now you can no longer get that stage 2. So for reverse engineers like us, when you spot a stage 2 like this, first step is go grab it, pull it down, and analyze it. The attackers here are able to kind of cut off that chain where we'd be able to get our hands on it if, say, we discovered the stage 1 at some point, right? Then, of course, with no surprise, the open command opens this newly unzipped application, which is why we see the internal PDF viewer immediately open after that. So make note, the open command, when you run it, it does cause the app that you're specifying to be opened in a new branch. It won't happen under the same tree. So now this malware actually waits to connect back to the attacker until a user loads a specially crafted PDF. The threat actors are very specific about their victims, and they only want that victim to connect back to the attacker if it's someone that they're expecting. So that's how this PDF that is sent to a user, which you're not seeing here, this is behind the scenes. The attacker provides an app and a PDF and say, if you want to decrypt this, it's important that you open it inside our secure app, right? Again, more on that at the talk. But it causes this PDF to operate like a bit of a key, and that they'll know only the right people are coming back because they're specific about who they send that PDF to. Another tool that we have is a timeline, which you see at the bottom of the screen here under the subtitles, but you can drag the timeline inside of SpriteTree to adjust the events of when you captured. So we see that after the PDF is loaded into the app, this results in a bunch of additional recon commands then being executed by the malware. So that's Rust Bucket. Again, deep dive there, Ballroom F, closely followed by this one, I think just maybe a half-hour break in between, but analyzing state-sponsored malware on macOS is the talk you're looking for that. So let's move into one last use case here, the Schleyer malware. I use this as an example a lot because it's basically a malware dropper that keeps up to date. It tries to evade antivirus at the same time generating a lot of system activity when you actually run it. So it kind of makes it a prime sort of use case for SpriteTree here. So because of this, one of the immediate things you should notice is how large the process tree kind of is that it generates. And in terms of Schleyer malware samples, in terms of the different Schleyer malware samples that are out there, this one's actually pretty small in terms of noise that it generates. I cut it off here before the final stage malware had executed. So an interesting thing that catches my attention within this capture is that most of this activity all occurs under a terminal. The reason I find this interesting is because a terminal is a tool that a user intentionally opens and uses, not one that gets open and run in the background, right? So oftentimes, activity occurring in a terminal is overlooked as though the user intentionally executed it. But if we take a look at the bash instance that spawned under the terminal, right, we go to that node, we click on the details, we see that it wasn't necessarily opened manually by the user. Instead, a file called install.command was run. A .command file, it's the same as a sh script, bash script, whatever, but if you were to double click on it instead of opening in a text editor, it launches in your terminal. So now we know we got a bash script that executed, and there's a lot going on in this tree. We showed you that we have the collapse feature, but and we showed you that we also have the ability to take the timeline that's down at the bottom, and we can kind of drag it back and focus on the order of events that carried out as the malware ran. So you can hear me, here you can see me dragging the timeline back, and as I rewind, we lose some of the nodes that weren't active at that time, right? So again, very helpful feature when you have a lot going on in a tree, or maybe you have multiple branches spawning commands all at once. You can kind of pinpoint the order that they happened without looking at the raw text. An interesting command that Schleyer uses on more than one occasion is the OpenSSL command. It uses this to actually decrypt an additional payload that comes packaged inside of its downloaded contents. It does this doing some easily reversible, but rather sneaky and stealthful enough approach. But ultimately, the data is retrieved, and then it's piped into a command that you see here, which takes a resting file full of encrypted bytes and decrypts them into a readable payload. We'll see OpenSSL again in just a few minutes, and we'll get more into it. Here's where the timeline actually gets pretty interesting. As we drag it along, we do see that some more malware commands are indeed spawning. However, we see that one of those commands that the malware runs is the kill all command. The kill all command takes an argument that you provide and it terminates it, as you might suspect by the name, right? The command that the malware runs is pointed at the terminal. And the idea behind this is that hopefully the terminal will run the bash script that the author has provided, and then it will immediately kill the terminal before the user sees the popping up of the terminal, right? Hopefully it will run it, finish it, and close it before the user is none the wiser. So at this point, you might be wondering to yourself, if technically a command was run to kill the terminal process, how is it, as we slide the timeline forward, we continue to see commands spawning under the terminal app? Well, let's quickly return to where we kind of were before, right? There's another command we saw run in our terminal. It's the no-hup command. And what the no-hup program does is basically it has the ability to disconnect you from your current process tree. So this is going to take all the arguments passed to it and run those commands under launch D instead. So the terminal can be killed, but the session will live on. Basically, it's a way to ensure that if somebody kills your parent, your program is going to keep running in some manner. That's why we continue to see additional commands spawning under the process tree. But provided with the no-hup command are a bunch of commands that you can see down in that bash-c command line. So what's it going on to do? Well, first, it's going to run the uname command, where we see CPU architecture is checked, also done by previous malware that we analyzed, right? According to the bash code here, if the CPU type is ARM, the malware will install Rosetta. More on that as we come up to it. Remember, we're just seeing the command get loaded. We haven't seen the nodes run yet. OpenSSL is called again. This time, it looks like it's used to decode a binary. We know this because we see that the arguments seem to specify an archive file being passed in, and then the file with the variable name bin file resulting as the final payload. Next, we see that Schleyer will clear the extended attributes from the file and give it executable permissions. Finally, we see that the decrypted binary is executed in the background. You see 2 ampersands kind of in the command, if you can read that. And then once it's running, the executable on disk will be deleted with the rm command. So this no-hup command is going to run, and we should be able to watch this all play out as we drag the timeline forward. First is the uname node that we see. And sure enough, that uname command does get run. It checks for CPU architecture. After this, we see it go on to run software update, the software update command. Now, we know because we have read the large one-liner what's happening, because the malware discovered this computer has an ARM-type architecture rather than an Intel architecture. It's now running the software update command. We can assume it likely has a final payload that's compiled for Intel, and clearly, this computer is running ARM. So the install Rosetta command ends up loading a PKG installer that's embedded with Perl scripts that assist with cleanup. This is a PKG Apple supplies, basically for convenience when you have an Intel binary and it needs to run on an ARM computer. So we kind of see that Schleier's like, oh, I see you have an ARM computer. I'll make sure to let this malware execute without a hitch for you. But this installer is the reason we see a whole series of Perl actions that end up getting carried out on the system. We see a lot of Perl scripts being run, and it's because the installer is not necessarily calling those commands. The malware is not necessarily calling those commands, but in fact, a PKG that Schleier is running to get this operational is what's calling those commands. So we'll then grab the timeline and drag it to the next set of commands that should be coming up to the OpenSSL command we know gets used to decode the executable. It's there. I know there's a lot of arguments there, but we've already kind of covered what's happening at this point, right? A binary is being decoded for the final payload. However, we know we shouldn't be done yet. We should see a newly created executable launch next, this new decoded binary. So as we go on to drag the timeline a bit further, sure enough, as expected, we see that this takes place as the decrypted binary. You can see here appears to have these random letters associated with it, right? It ran multiple times, created multiple children, and it's going to do a lot of different things to grab URLs from some of your history that it's then going to re-communicate with using, once again, the curl command. When it comes to detections, watch in your environment what's happening in curl. I cannot stress that enough. Curl is used constantly for malware, APT, adware, whatever it be. It's constant. So anyway, we see that gets used as the next step, and it's now going to download additional payloads and run those. The good news is we can see where these curl commands are reaching out to, right? And as I stated, we're going to go to these addresses, pull down stuff, and start looking at it and reversing it and seeing if there's anything actually of interest here. Ultimately, Schleier, the final payload is going to be adware that it installs on installation, where the authors then gain some type of royalties for whatever ads pop up on the screens, depending on if the user clicks them. Maybe you get some type of benefit if you manage to land on an additional endpoint as a malware author. It's kind of hard to tell where everything goes from here, but Schleier is a rather sneaky dropper for being, and up-to-date dropper for being just adware. So, when can you have it? Well, we're looking to release SpriteTree the week of October 9th, and it will be available basically for download on my website, once again, so themittenmac.com. Be sure to check out that as well as some of the blog posts. As we're going to release some blog posts that'll kind of recap on some of this because we know it's a lot of detail. You got to first do the capture, and then you can do the analysis, so we'll get some of that going. Yeah, be sure to check that out to kind of recap on some of the technical details.
So we'll be releasing it then as a free community tool to help others learn about macOS security and how the operating system generates events. So keep an eye out for our tweets for more details on that. And do we have time for questions? We've got.
I'm not sure we have time for
3
questions.
minutes. Yeah.
We'll ask Eric.
I know everything, maybe. Yeah, I think we can get a couple in. So awesome presentation. That was fantastic. There were a handful of questions that came in. Before we do that, though, because we are short on time, when they have more questions, where can they find you?
Yeah, we'll stand right outside for just a few. If anybody has additional questions, we'll be right outside the door.
Awesome. So Why did you decide to use SpriteKit instead of some other framework, or what made you think of using that in the first place?
Yeah, that might have come around. It might have come around earlier before we addressed that. But the essentially it was because we had done some development before using D3 is a popular one when it comes to JavaScript. If anybody's done this kind of tree development before, but ultimately it's all JavaScript. If you've ever tried to write JavaScript inside a macOS app, it is not a fun experience, and I would not recommend it, but it is doable. But ultimately, this gave us full control over how we wanted to display data and how we wanted to interact with it.
So then I guess a follow-up to that would be on performance. So when you're viewing a large amount of trees or collecting data for a long amount of time, what does the performance look like?
Yeah, that's a great question. Right now, we do kind of have it designed and geared towards smaller captures, like malware detonation. I'd argue we have seen if you take a massive timeline and you load it in, it will work. You might be running your CPU pretty hard, and it might matter the amount of RAM that you have. They are issues we're also looking at and going to fix in the future to hopefully adjust for, because you can run ESLogger as long as you want, right? Capture as many events as you want. We are hoping to adjust it and optimize it so that you can take larger captures. Right now it is geared towards maybe 2-3 minute captures, something like that. So,
but it's a high priority fix to address the performance.
Cool.
Yep.
For larger captures.
So obviously a ton of really good information here, specifically around just evaluating malware. But somebody who's also wondering extending beyond that, and how can these folks take this information home and maybe use this in real world examples? Any thoughts on that?
Sure. Yeah, that's the loaded question of macOS security and how do you get into it, right? Ultimately, the best way to play with it is to grab ESLogger. Again, as Maggie said, it's on Ventura, right? It's on any operating system, Ventura or later. So you can just run ESLogger, capture some events, run your own commands like Maggie showed you when she was walking through it, and just see how that formats in the tree. If you have a question around, for example, you come back to the Etsy sudoers file being modified. Go modify the Etsy sudoers file, organize by the different trees, figure out how the software in your environment, whatever you're using for endpoint security, figure out how you can make those same relationships. It is possible to match those same relationships and build some of your own detections, whether it be in the cloud, in your product, whatever it is. Really, it's just getting hands-on and playing with it. If anybody wants to get more into kind of the malware side, Patrick Wardle has a good book. A lot of people are familiar with it, The Art of Malware. That's kind of a good introductory. Gets a little heavy on the reverse engineering side if you're into that, but there's also a lot of good kind of higher level notes as well. So.
Awesome. Well, great job, both of you, and thanks for a great session. Thanks, everyone.
Cool. Thank you.